A gravitational singularity, spacetime singularity, or simply singularity is a condition in which gravity is predicted to be so intense that spacetime itself would break down catastrophically. As such, a singularity is by definition no longer part of the regular spacetime and cannot be determined by where or when. Gravitational singularities exist at a junction between general relativity and quantum mechanics, therefore, the properties of the singularity cannot be described without an established theory of quantum gravity. Trying to find a complete and precise definition of singularities in the theory of general relativity, the current best theory of gravity, remains a difficult problem. A singularity in general relativity can be defined by the scalar invariant curvature becoming infinite or, better, by a geodesic being incomplete. Gravitational singularities are mainly considered in the context of general relativity, where density would become infinite at the center of a black hole without corrections from quantum mechanics, and within astrophysics and cosmology as the earliest state of the universe during the Big Bang. Physicists are undecided whether the prediction of singularities means that they actually exist or existed at the start of the Big Bang, or that current knowledge is insufficient to describe what happens at such extreme densities. General relativity predicts that any object collapsing beyond a certain point, for stars this is the Schwarzschild radius, would form a black hole, inside which a singularity, covered by an event horizon, would be formed. The Penrose-Hawking singularity theorems define a singularity to have geodesics that cannot be extended in a smooth manner. The termination of such a geodesic is considered to be the singularity, the initial state of the universe, at the beginning of the Big Bang, is also predicted by modern theories to have been a singularity. In this case, the universe did not collapse into a black hole, because currently known calculations and density limits for gravitational collapse are usually based upon objects of relatively constant size, such as stars, and do not necessarily apply in the same way to rapidly expanding space such as the Big Bang. Neither general relativity nor quantum mechanics can currently describe the earliest moments of the Big Bang, but in general, quantum mechanics does not permit particles to inhabit a space smaller than their wavelengths. Many theories in physics have mathematical singularities of one kind or another. Equations for these physical theories predict that the ball of mass of some quantity becomes infinite or increases without limit. This is generally a sign for a missing piece in the theory, as in the ultraviolet catastrophe, renormalization, and instability of a hydrogen atom predicted by the Lama formula. In classical field theories, including special relativity but not general relativity, one can say that a solution has a singularity at a particular point in spacetime where certain physical properties become ill-defined, with spacetime serving as a background field to locate the singularity. A singularity in general relativity, on the other hand, is more complex because spacetime itself becomes ill-defined, and the singularity is no longer part of the regular spacetime manifold. In general relativity, a singularity cannot be defined by where or when. There are different types of singularities, each with different physical features which have characteristics relevant to the theories from which they originally emerged, such as the different shape of the singularities, conical and curved. They have also been hypothesized to occur without event horizons, structures which delineate one spacetime section from another in which events cannot affect past the horizon. These are called naked. A conical singularity occurs when there is a point where the limit of some diffeomorphism invariant quantity does not exist or is infinite, in which case spacetime is not smooth at the point of the limit itself. Thus, spacetime looks like a cone around this point, where the singularity is located at the tip of the cone. The metric can be finite everywhere the coordinate system is used. An example of such a conical singularity is a cosmic string and a Schwarzschild black hole. Solutions to the equations of general relativity or another theory of gravity, such as supergravity, often result in encountering points where the metric blows up to infinity. However, many of these points are completely regular, and the infinities are merely a result of using an inappropriate coordinate system at this point. In order to test whether there is a singularity at a certain point, one must check whether at this point diffeomorphism invariant quantities, i.e. scalars, become infinite. The regularity becomes evident when changing to another coordinate system, such as the critical coordinates, where the metric is perfectly smooth. On the other hand, in the center of the black hole, where the metric becomes infinite as well, the solutions suggest a singularity exists. The singularity occurs on a ring, a circular line, known as a ring singularity. Until the early 1990s, it was widely believed that general relativity hides every singularity behind an event horizon, making naked singularities impossible. However, in 1991, physicists Stuart Shapiro and Saul Tucholsky performed computer simulations of a rotating plane of dust that indicated that general relativity might allow for naked singularities. It is hypothesized that light entering a singularity, thus making the naked singularity look like a black hole. This concept demonstrates that black holes radiate energy, which conserves entropy and solves the incompatibility problems with the second law of thermodynamics. Entropy, however, implies heat and therefore temperature. The loss of energy also implies that black holes do not last forever, but rather evaporate or decay slowly. Black hole temperature is inversely related to mass. This will occur at a cosmological redshift of more than 1,000,000 or so since the background radiation formed.